learning everything properly, and also you would have completed the 3 assignments without too much difficulty by now. Yes?
Yes, sir.
Yes.
Okay, very good. So today's session, we will look ahead on the applications of differentiation and differential calculus into understanding various properties of functions other than just calculating the instantaneous rate of change or slope of tangent. What other information about a function we can get from calculation of its derivative or differentiation? Okay, so behavior of a function from its derivative. What we can understand about the behavior of the function. Let's understand that aspect next. So we have a function y is equal to fx, and we know that the derivative of the function f prime x comes from differentiation. So what information about the function we get from this? So apart from first thing, the slope of tangent at any point, obviously. So at a specific point, let's say x equal to a, the slope of the tangent is equal to the value of the derivative at that particular point. Okay. So this is something very obvious, that information we get. But apart from that, so if we look at let's say a hypothetical graph of a function, which is like this, let's say. Now let us say this specific point is A, this specific point is B. So what we are seeing is that if we draw the tangent at any point like this, which is before A, you'll get this sort of a tangent line, which as you can see has a positive slope. Whereas if we draw the tangent at any point between A and B, in this particular case, you see that we get a tangent line with a negative slope. And again, if we draw after B, you can see we'll get a tangent with a positive slope again. So in general, the algebraic sign of, so if this is the graph for some particular function y equal to fx, what we can see is if the slope of the tangent is positive at a particular point, that means in that set of values of x, the value y is increasing with respect to x. Okay. So for example, here in this example, for x less than a or x greater than b, we can see that y is increasing with x. So what that means is that if we increase the value of x, okay, the value of y that increases. So when this happens, it also implies that for the same interval, x less than a or x greater than b, f prime x or the derivative is a positive quantity. That is, in other words, the slope of tangent that will be a positive quantity at any point where the function is increasing. So that is one important piece of information we get. And the reverse of that, that if the function is decreasing in a certain interval, like between a and b, you can see over here that the function is decreasing. So when we increase the value of x, the value of y is dropping. So at such a point, in an interval where the function is decreasing, if we draw tangent, it should have a negative slope. Okay. So just like for an interval where the function is increasing, the slope of tangent or the derivative is positive. Like that, for an interval where the function is decreasing, the slope of the tangent or the value of the derivative will become negative. Just make a quick note of this point, then we'll understand more about this with some examples. So by analyzing the algebraic sign of the derivative, whether it is positive or negative, we can get an idea about whether the function is increasing or decreasing in a given interval. So that is the point I'm trying to get at over here. Okay. Yes, Nishchay, that's correct. We will be coming to the point of local maxima and minima also through this. So as you can see in this particular graph that I've drawn, we will define the point x equal to a as a point of local maxima. And similarly, the point x equal to b will be defined later as a point of local minima. Okay. But before we come to the exact definition of what is local maxima and local minima, let us understand this other interesting aspect first, that without worrying about maxima minima, if I just look at the algebraic sign of the derivative, whether it is positive or negative, I can get some useful information about the function at for that set of values of x or for that interval of x. Okay, so now likewise, you can also see in this above example, for x lying anywhere greater than a but in b. Y is what we said decreasing with respect to x. That means that the value of fx will decrease with an increase in x. So when that happens in a certain interval, we say that the function has a decreasing nature. You can also see that that implies that the derivative will be negative for this interval. That is, the slope of tangent is negative for any x such that x is between a and b.
But f dash or y is increasing near b, right? We cannot say exactly that it's decreasing.
So here what I've assumed is not that the shape of the graph it is like this, that it sort of just dips at b. So that exact point where it reaches the, you can say, the trough of the valley, that point is b. You understanding now? So if I take a point even like infinitesimally before b na, we say x delta x tending to 0 भी कम मैंने लिया, तो वहां पर भी उसका slope कैसा होगा? Negative होगा. Whereas the moment I cross the point b and go beyond it, even by delta x tending to 0, the slope will again become positive. So that's the assumption that I've taken in this graph. Okay, that b is that dip point.
So before that, the tangent is decreasing, and just
before that the tangent is negative and the function is decreasing, because it reaches the local minima. Later we'll see that at the point b it reaches the value which is the local minima. So before that it's decreasing and after that it is increasing. So that is why notice in this interval I have not included the point b. It's not less than equal to b, it's less than b. So less than b means all real numbers which are less than b. So you can go up to delta x tending to 0 before b, but you cannot go up to x equal to b. So that's where the concept of number line also becomes little abstract. That if we take any two numbers, in between them there are infinite number of real numbers.
Sir, if we find the rate of change of tangents, so then it actually means we are differentiating f of x No,
F-
we're differentiating the derivative of f of x, right?
Yes, in fact, we will see that term today. You might have heard the term, it's second derivative. No? If you read
Yes, sir,
ahead
that's
or
Yes,
the
so.
differentiation.
So there's
second order
something called
derivative.
second derivative, or in short form, we write it as f double prime x. So that means the rate of change of rate of change. So that means, if we have a function, let's say x squared, its derivative is what, 2x. So then what is its second derivative? It's the derivative of 2x. So that's 2. Or if we have, for example, sine x, the derivative of sine x is cos x. But the second derivative will become the derivative of cos x, which will become minus sine x. So at this stage, when I'm just saying out loud, it might seem a little confusing, but we will see today that that's also another interesting property of a function, that what the second derivative tells us, not only what the derivative tells us, but what the second derivative tells us. But let's first organize this information and also see an example. So in general, what we can say that if for a function y equal to fx, okay, the derivative f prime x is positive in a certain interval. So interval means set of values of x from some initial point to some final point. Okay. Then in that interval, what is happening? The function is increasing. Okay. So I will use the symbol like this for increasing. That means the function is increasing. And what means we mean by increasing is that when we increase the value of x by a positive value, when we change the value of x by a positive value, the change in y will also be positive. Okay. And the reverse of this, that if the derivative is negative in a certain interval, okay, then the function is decreasing in that interval. Okay, so let's look at an example of the application of this. Let's look at this function y equal to x cube minus 3x plus 2. Now we want to find the interval or intervals in which the above function increases or decreases. And let's say the domain set that we are taking over here is that x belongs to minus to plus infinity. So we have not put any boundation on the value of x. Now that doesn't always happen. For example, if we are practically using a function in physics and x represents time, then generally we will not take time in the negative domain. We'll take time only from 0 to infinity. But here we are just assuming that x need not be time. It can be any type of parameter, or it can be just a pure number. So there's no boundation on x. So it can go from minus to plus infinity. Okay. So in that entire domain of x, so the values of x that we take for a function in official language of calculus, that is called domain of a function. Okay. Domain is the set of values of the independent variable x. So for a function y is equal to fx, okay, this becomes, whereas the range of the function is basically the set of values of y. So some functions have an extremely short range, like sin x has a range, y equal to sin x has a range between -1 and +1 only, inclusive of -1 and +1. But certain functions have infinite range, like any linear function has an infinite range with an infinite domain. Whereas certain functions might have restricted domain, like y is equal to square root of x. The domain is non-negative numbers. We cannot take negative number in the domain. And the range also accordingly becomes non-negative numbers. Okay. So the domain and range actually depend on the nature of the function, okay, the definition of the function itself. Okay, anyhow, let's come back to this one. So how will we find the interval in which the function increases or decreases, or if there are multiple intervals, how will we find that? So we'll be using this concept. So for the given function, first thing we need to do is we need to find the derivative, and then we need to solve the derivative as an inequality, that in which part that derivative is greater than 0. So that inequality will give us an interval in which the function is increasing, and in which part the derivative is negative. So that inequality will give us the second interval where the function is decreasing. Okay. So let's try this out. So the function here is x cube minus 3x plus 2. So the derivative of the function is what? 3x square minus 3, which we can write as 3 into x minus 1 into x plus 1. So we can see that f prime x is greater than 0 for either x greater than 0, greater than 1, or x less than minus 1. So we say that for all x from minus infinity to minus 1, union with 1 to infinity, the derivative is positive, which means that the function is increasing in nature. So just a word about brackets that we use. Okay, if we say x, okay, so this is read as belongs to, okay, and this is read as interval x equal to a to x equal to b, but not including a and b. Okay. Whereas if we use a curly bracket, it will be inclusive of a and b. So this kind of a symbol means that x is greater than equal to a and less than equal to b. So this is called a closed interval. In maths, this is called a closed interval because it includes these values, whereas this one above, it is called an open interval. Just as your general knowledge, there is also something called a mixed interval, which is something like, the closed interval is not the curly bracket. The closed interval is the box bracket.
Square bracket.
Yeah, square bracket or box bracket. And this symbol, which looks like an epsilon or strange kind of an E, it is called belongs to the interval. Okay, so box bracket or square bracket implies closed interval. So if we have a mixed interval like this, A and then B with a normal bracket, this means that X is inclusive of A but exclusive of B. Okay. Now you might ask the question, okay, if it does not include B, then up to how close we can come to B? So for that, the answer is we can come up to infinitesimal. So for example, between B minus 1 and B, there are infinite real numbers. Between B minus 0.001 and B also, there'll be infinite numbers. Okay. So that is a bit of an abstract thing about the real number line, that between any two real numbers, there are infinite real numbers. Anyway, without worrying about that too much, let's come back here. So we can also say that, yeah, this is another way in which we can express the same thing. Okay. Say that for x greater than 1 or x less than minus 1, it means that it is for all values of x in the interval minus infinity to minus 1, open interval, union with 1 to infinity, open interval. So this means the same as this. When we say this and this, it means this union. Okay, so hope it is clear to all of you how this is coming up, because we've got the derivative as the product of these two things, x minus 1 and x plus 1. Now you can see that for x less than minus 1, both of these quantities are negative. So the product becomes a positive quantity. Whereas for x greater than 1, both of them are positive. So the product becomes a positive quantity. Whereas the moment we take x in between minus 1 and 1, you can see that x minus 1 will be a negative quantity, whereas x plus 1 will be a positive quantity. So their product will become negative. So the function is increasing in this interval before -1 and after 1. Okay. Whereas now if I analyze where the derivative is negative, I'll get this relation that 3x square minus 3 should be less than 0, or should be less than 0. So that means x should be greater than -1 but less than 1. Or we can say that for x belonging to the open interval -1 to 1, fx is decreasing in nature.
Sir, can you zoom out a bit?
Yeah. This is fine now?
Yes.
Yes, sir.
Okay, now let's try to analyze this information, and from this let's try to understand the graph. Okay, I mean, though it's not really important for us to be able to plot very accurate graphs, but let's see how this information helps us in visualizing the graph of the function. Okay, so next, to visualize the graph of this function, y is equal to x cubed minus 3x plus 2. Okay, so first thing we understand that if we just draw on a number line, we can see that in this part, the function should be decreasing. Oh, sorry, the function should be increasing. Less than -1, the function should be increasing. Okay, then between -1 and 1, the function should be decreasing, and then again after 1, the function should be increasing. Okay, that is the nature of the function, that x less than -1, the function is increasing. Then x between -1 and 1, the function is decreasing, and then at x greater than 1 it increases. Okay, that's one thing you can see. Okay, then so that we know from the derivative. Then another thing we know is that as x tends to minus infinity, what is the value of the function? It tends to minus infinity, because remember, what is the function? The function is x cube minus 3x plus 2. So this x cube term will dominate. Like think of a value of x like minus of 10 raised power minus 10. So what will be the value of the function? It will be minus of 10 raised power minus 30 plus 3 into 10 raised power minus 10 plus 2. So that's more or less equal to minus 10 raised power minus 30 only, no? Because this thing is negligible compared to this. So as x is a very large negative number, the function's value also becomes a very large negative number. And similarly, as x tends to infinity, the value of the function also tends to infinity. Because again, x cube dominates over 3x as x becomes very large. So instead of minus 10 raised power minus 10, if I take an x as 10 raised power 10, then we'll see the value of the function or y would be nearly 10 raised power 30. So that's another thing we can see as a trend about the function, where it is going as x is tending to minus infinity or plus infinity. So with this now we can do a bit of guesswork, and we can understand that the point -1 is rather special, because up to -1 the function is increasing, and after -1 the function is decreasing. And again, like that, 1 is very special, because up to 1 the function is decreasing, and then again it starts increasing. So it's dropping the values. Okay, so let's check out some values in between also. So for example, what is the value of the function at -2? Can you check and tell me? It will become -8, right? Plus 6 plus 2, so it's 0. Okay, what is the value of the function at -1? It is -1 plus 3 plus 2, so it is plus 4, right? What is the value of the function at 0? It is 2. What is the value of the function at 1? It is 1 minus 3 plus 2, so that's 0. Okay, what is the value of the function at 2? It plus 2, right? So 10 minus 6, so that's plus 4. Okay, let's check out two more values. What is the value of the function at -3? So that is -27 plus 9 plus 2. So -27 plus 11, so that will be minus of 16. And similarly, let's check the value of the function at 3. So we'll see it 27 minus 9 plus 2. So 29 minus 9, so it's plus 20. Okay. So now we have a bit of information further, okay, and we can now attempt to sort of draw a rough kind of graph. So keeping all this in mind, all this information that I put together, that first of all, this point -1 is rather special, because up to -1, the function is increasing, and after -1, the function starts decreasing. Similarly, the point +1 is rather special, okay, because up to +1 it decreases, and then again it starts increasing. Okay. Okay. So now let's start plotting the values that we have got here. So at -3, the value is some -16. So let's say it's over here. Then by the time we come to 2, it's 0. Okay. And by the time we come to -1, it has gone up to 4. So let's say it's somewhere here. Okay. So my graph is obviously not up to scale. I'm drawing a very rough sort of graph. Okay. Then by the time we come to 1, okay, or the function has reduced to 2. So it's somewhere here, let's say. Okay. Then by the time we come to 1, the function has become 0. Then by the time we go to 2, it's again become 4. So it's here. And 3 is become much larger, so plus 20. just like this. Okay, so we can roughly say that the function, and of course as x is tending to minus infinity, it is minus infinity, so it should be coming from minus infinity like this. Oh, sorry, slightly different. At 1 it was going to 0. So it continues to decrease. Okay, at 0 it is 2, but then it continues to decrease, goes up to 0 at 1. And then it goes like this. Okay. So, in a more naturally drawn shape, let's attempt this graph once more. So let me first draw the graph and then put the values. So it seems to be doing something like this, the graph, where this point is 1. This point is minus 1. This is 2. This is 4. This is 2. At 3, it was going much beyond. So, for example, this was minus 2. And at minus 3, value was minus 16 or something. So something like this, where so now you can see all the properties of this function that we had seen earlier. So we'd seen that the derivative of the function so from this, what we had learned that the function was increasing for x belonging to minus infinity to 1, to minus 1, which you can see in the graph. Till you are reaching minus 1 from minus infinity, the slope at all these points is positive. But at 1 exactly, we can't say it's positive because it becomes a flat line. Okay. Then again, the function is decreasing as you go from minus 1 to 1. So that is this part. You can see anywhere here, the slope is negative. But then again, the function increases for x going from 1 to infinity. That's one thing. Okay. And then, of course, the specific values that we had seen for x equal to 0, the value of y was 2. For x equal to minus 1, the value of y was 4. For x equal to minus 2, the value of y was 0. Minus 3, the value was minus 16. Plus 1, the value was 0. 2, the value was 4. And 3, the value was 20, if I remember correctly. Yeah, 0, 4, 20. Okay. So, and also, very importantly, that when x tends to minus infinity, the value of y also tends to minus infinity, which you can see in the graph, that this line will go up to infinity on the negative side, and on the positive side also it will go up to infinity. So as x tends to infinity, y tends to infinity. So you can see, even without talking about maxima minima concept yet, or slope of tangent being 0 at some turning point, or even without these type of concepts, just by analyzing the sign of the derivative, that where it is negative, where it is positive. So here the derivative is positive, greater than 0. Here the derivative is less than 0. Here the derivative is again positive. So just by analyzing these 3 pieces of information and plotting a few of these points. Okay, I've got a rough estimate of how the graph should look like. So that is one of the wonderful things about differential calculus and how it helps us to analyze a function. Now, if you think about it, this is quite a complicated function. It's x cube minus 3x plus 2. So it's a degree 3 polynomial, which has some in-between terms also. It's not like a single x cube term or something. So it's not something exactly very straightforward. But just by using this simple concept that the derivative is positive in an interval where the function should be increasing, the derivative is negative where in an interval where the function is decreasing, you can see we are getting all this information about it. Of course, along with the help of a few values also. Okay. But we are getting a basic idea of how the shape of the graph should look like. So I'll just scroll up a little bit and take down the key points over here. Okay. I'll also tell you an easy method of solving an equation like this. This type of equation, it is called an inequality. So we will look at, so this is an inequality, because we are not equating it with something. We are saying it is greater than or less than. So such an equation is called an inequality. So I'll just give you a few tips of how to solve an inequality also. In fact, there is an entire chapter in your algebra and mathematics called inequalities, where you will learn a lot of advanced methods of how to solve inequalities. But that will come later in your math syllabus. So we will see just a few tricks over here of how to solve inequalities. So the algebraic sign of the derivative, that itself is something very useful for us. In generally trying to understand the nature of a function, the trend of a function, how it behaves in a given interval, just the algebraic sign gives us some useful information, as you can see. Okay, so once I have solved the inequalities to get these intervals, where the function is increasing, so that is less than -1 or greater than 1, and where the function is decreasing, it is between -1 and 1. The open interval between -1 and 1. Open interval means not including the points. Closed interval means including the points. Okay. So open interval -1 to 1 is the one where the function is decreasing. Okay. Up to -1, the function is increasing. After 1, again, the function is increasing. So this gives me this sort of idea that on the number line, in which region I should expect the graph of the function to rise, in which region I should expect the graph of the function to drop. So that is this information which I've just put together in this visual over here. Now, along with this visual, if I just take some arbitrary values, including trying to understand what happens when x is minus infinity or when x is tending. So that gives me the endpoints of the graph, how it should go. And along with that, I've just arbitrarily taken some more points. If I'd taken larger number of points, my graph would be that much more accurate, but it would take me that much more time to solve the graph also. So I've just taken an optimal number of points over here, which is, I think, 7 points in all. And if I include minus and plus infinity, so I've analyzed the function at a total of 9 points. So just by doing this simple analysis, that I took 7 values of y for 7 conveniently chosen values of x from -3 to 3, and I have this information above, that on the number line I have an idea of where the function is rising and where the function is dropping. So just putting together these two information, see, I've come up with quite a decent graph of the function. It's giving me quite a lot of helpful information about the function. Okay. So this is one of the scopes of differentiation, that what is the scope of analysis we can do with differentiation. This is part of that scope of analysis. Okay, now as I told you, I'll just give you a tip about how we can solve an inequality like that one easier. Okay. Solving an inequality of the type, let's say x minus a into x minus b is greater than 0 or less than 0. So for example, we had that one, that 3x square minus 3 was greater than 0, or 3x square minus 3 is less than 0. So we want to find the values of x. So when we factorize it, we saw that it is, okay. So now see, since 3 is a number greater than 1, so 3 into x minus 1 into x plus 1 is greater than 0, implies that x minus 1 into x plus 1 is greater than 0. Okay. Now how to solve this interval? Okay. So what we can do is we can develop something called the number line method of solving the inequality. Some of you might be familiar with this, some of you might not be familiar. So just let's go over it.
Sir has taught us this yesterday.
Acha, you have learned
Last
the number
class.
line method. Okay, so very good. So in the so now you can easily understand what I'm doing over here. So in the number line method, what I will do is, now see, for each of these brackets, the critical point for x minus 1, what is the critical point? It's 1. And for x1, what is the critical point? It is minus 1. So if I analyze this quantity x minus 1, it is negative up to 1 and becomes positive after 1. And if I analyze x plus 1, it is negative up to minus 1 and it becomes positive after minus 1. Okay. So this is the nature of this. This is the nature of this. So now when we want to look at the nature of their product, okay, so when we analyze x minus 1 into x plus 1, now I can see that their product is positive in this region. Their product is positive in this region, but their product is negative. So this is a very convenient and easy method in which you will never make a mistake with solving an inequality. And if your inequality has now more terms, like it's x minus a into x minus b into x minus c upon x minus d, let's say, this has to be greater than 0, then you'll just have more number of terms over here. Okay, so when you solve it, you will have to take the critical points a, b, c, d like this and analyze each of these brackets. And then from that, you'll have to see. So I'm sure you've done things like this. So this is now showing you that this quantity x minus 1 into x plus 1 is greater than 0 for x belonging to the interval of minus infinity to minus 1 union with 1 to infinity. Okay, this region here and this region. Whereas it is negative for the interval minus 1 to 1. And also it is showing you that it is 0. I mean, which is an obvious thing for two values of x, plus minus 1. So in this case, it's pretty obvious, but in case the inequality becomes something more lengthy, then this number line method becomes very, very useful. Okay. So hope this is all clear. So let's do a couple of questions more for practice before we come to the next concept, which will be about maxima minima. Find the intervals for which y increases with respect to x and y decreases with respect to x. Now let's do another example. Now this one is a little more interesting. Sine square x minus sine x. Okay. And let's take a limited domain. X is from 0 to t. So find again intervals for y to increase or y to decrease. Okay, just give both of these a quick try. We'll discuss. Yes, Nishya, this is also called the Wavy curve method. I think that is the technical name for it in algebra. Okay, so just give it a try, these two questions. Yeah, so Nishya, I think what we want to say over here is that y is increasing for that interval and decreasing for that interval, right? Not whether
Sir,
y is positive or negative.
acha. Oh, sorry.
Got it, na? There's
Yes,
a
sir.
difference between the two, na? यहाँ पे that's a different thing. If I want to ask where y is positive, then you have to solve the inequality that x square minus 3x plus 1 should be greater than 0 or less than 0. That is going to give us a different thing, okay? But here I'm asking where the y is increasing with respect to x. So what I mean that dy by dx or derivative of y, that should be positive. Or where y is decreasing, the derivative should be negative.
Acha, okay, sir.
What, na? They're two separate things, no?
Yes.
Yeah.
So done.
Okay, very good. So Nidhish, check your values once, but Aparna, correct. Chinar, correct. Dhruv, correct. Nishchay, correct. Ibrahim,
So that's a mistype, sir. I'm typing.
okay. Okay, so let me just work out the first question and give you the answer. So the first question, this should be y is increasing when x belongs to the interval 3/2 or 1.5 to infinity, whereas y is decreasing for the interval minus infinity to 3/2 or minus infinity to 1.5. Now this one will be a little bit more complicated. We'll come to that. Okay. So let's analyze how we solve the first part. Y is equal to x square minus 3x plus 1, or the function is equal to x square minus 3x plus 1. So the derivative of the function is equal to 2x minus 3. So now the function increases for f prime x being greater than 0. So 2x minus 3 being greater than 0. That means x being greater than 3/2, or x belonging to the interval from 3/2 to infinity. Okay. Whereas the function decreases for the derivative being negative. So equally simple, 2x minus 3 being negative means that x should be less than 3/2, or x should in general belong to the interval minus infinity to 3/2. So if we also try to visualize this information on a number line, we can see that the function has this kind of trend. There's only one critical point, and that critical point is 1.5 or 3/2. So the function is decreasing before this and is increasing after this. That's this function. Come to side. So we'll see in a bit like how we can use this information to get some more complete graphical analysis also of the function. Okay, but yeah, Nidhish, you understood now? Okay, good. So Ibrahim, this is clear now?
Yes, sir. I got this one.
You got this one, no? Okay. Yeah, right. You got the answer for this one. Yeah, I think most of you who sent me the answers got it correct. Maybe one or two people. Yeah, Abhinav, the second one appears to be correct. I'll just verify for you. Okay. Okay, now let's come to the second one. So the function we have over here is sine square x minus sine x. Okay, but for a limited domain that x is from 0 to 2 pi. But what we can also understand that in this domain, sine x's value ranges between 1 and -1. So we should be mindful of this also. Okay. So now let's come to it. So dy by dx, or the derivative of the function, is basically what? Derivative of sine square x, which is 2 sine x cos x, minus derivative of sine x, which is cos x. Okay. So please let me know if anybody has a doubt in any of the steps, including this differentiation step, because I'm doing few steps directly now. Okay. So sine square x's derivative I've done directly as 2 sin x cos x. Now instead of writing this as sine 2x minus cos x, I will write it in the more convenient form as cos x into 2 sin x minus 1, because that will help me analyze the algebraic sign better. Okay. So now I can see it is the product of two things like this. Okay. Where, oh sorry, I missed out the x. Yes, Nishchay, you have a doubt, beta?
Sir, what if we do it by sine 2x minus cos x equal to 0? Why will it be wrong?
It will not be wrong, beta. It's just that it will be difficult to analyze. Okay. I'll show you why. Because we can also, like, you can also write this as f prime x is sine 2x minus cos x. But now when I solve the inequality, that when it is greater than 0, when it is less than 0, I'll have to compare that when sine 2x is greater than cos x and when sine 2x is less than cos x. So that will become a little problematic, isn't it, in comparison to this?
Okay, sir.
Here you can see it's a product of two things. So it's easy to analyze when cos x is negative, when cos x is positive, when this bracket is negative, when this bracket is positive, isn't it?
Yes.
Understanding the point? Okay. So now, for example, if I want to solve for, therefore, if f prime x is greater than 0, so it means that cos x into 2 sin x minus 1 should be greater than 0. Okay. Now let's understand each of these terms individually. So cos x is varying with respect to x in this domain. So if you look at cos x from 0 to 2 pi, we know that cos x is what? It is plus 1 here, it is 0 here, it is minus 1 here, it is 0 again here, it is again plus 1. So in between, it has positive values here, then it has negative values all the way here, and again it has positive values. Okay. Now the more tricky one is the second one. If you look at this function, 2 sin x minus 1. Now what we can say about this? Okay. It will be positive where sin x is greater than half. Okay, whereas it will be negative where sin x is less than half. So from 0 to 2 pi, if I analyze sin x, so the critical point for me becomes pi by 6 or 30 degrees. Okay. And again, 5 pi by 6. These two become critical because sin x is half over here. Okay. And again, half over here. And then there are two more values which are critical. And that is,
Sir, 5 pi by 6
5
is
pi by 6
minus
is
half.
before pi. No. 5 pi is minus half. Okay. So this point is how much? It will be 2 pi minus pi by 6. So it will be 7 pi by 6. 7 pi by 6, again it becomes half, no? No. Sign
No,
is
sir,
negative in this quadrant. It is minus half over here. So this point is not important. It's positive in second quadrant only. So 5 pi by 6 was the correct value. I've just taken it. So at this value, it is half. This value, it is 0 again. Here it is minus 1. So these all values are negative. These values are positive. But here is going from half to 1. Then again coming down from 1 to half. I mean, this is easier to understand from the graph actually. So now what I can say about this term, 2 sin x minus 1, when will this be positive? It will only be positive when sin x is greater than half. No? So that will be positive only here, only in this part. Because before pi by 6, you can see that the value of sin x is less than half. So this is negative. Between 5 pi by 6 and pi, again it's between half and 0. No? So again this is negative. And this part of sin x is only negative. So obviously the whole thing is negative. Okay, so getting this now. So this bracket, this has this kind of trend. And this one, this factor has this kind of trend. So now we can say about their product what is happening.
Sir,
So
can you
that
explain
we
from
get
the
by merging the
interval?
numbers. Yeah, beta?
Can you explain from the interval pi by 2 to 5 pi by 6?
So as I said, that will be easier to understand if you just visualize the graph of sin x. How does the graph of sin x look? It looks like that a typical wave which increases from 0 to 1 in the first quarter cycle, right? Pi by 2, then decreases back to 0 in the next quarter cycle. That is pi by 2 to pi, then decreases to minus 1 in the next quarter cycle, and so on and so forth. So if we are just looking between 0 and 2 pi, the graph of sin x, that is something like this now. It's like this. So this point is pi by 2, this point is pi, this point is 3 pi by 2. This point is 2 pi. But now see, we are interested in which thing? We are interested in 2 sin x minus 1. So this 2 sin x minus 1, for this 2 sin x minus 1 is greater than 0 when sin x is greater than half. Okay. Whereas 2 sin x minus 1 is less than 0 when sin x is less than half. For us, the critical value of sin x is how much? It is half. So, this value is 1. This value is minus 1. So sin x is overall ranging between minus 1 and plus 1. But what about this whole term, 2 sin x minus 1? So for that, the critical value of sin x is what? It is half. So the moment the value of sin x goes greater than half, what happens? This whole term becomes positive. So that is in this region. That is in this region. Whereas for any other value of sin x, which is less than half, this whole bracket will become what? Negative. So for us, which are the critical points on the x-axis? These are the critical points. Sine 30 or pi by 6 and sine of 180 minus 30 or 150 or 5 pi by 6. These are the critical points. So from this graph now, what we can understand that sine x is greater than half for x belonging to this interval. 0 to pi by 6 union with 5 pi by 6 to pi. These two small intervals, this one here and this one. Whereas for all other values of x, you can see from 0 to 2 pi, sin x is less than half.
Sir, it should be for x belonging to pi by 6 to pi by 2, right?
Oh, sorry, sir. Yeah, I've taken the opposite. Greater than Liana. So actually, I'm talking about this interval, this one. Correct. Okay. So this is for open bracket 30 degrees or pi by 6 to 150 degrees or 5 pi by 6. Whereas now for this other brackets, which I was writing earlier, 0 to pi by 6, okay, union with now it will become 5 pi by 6 right up to 2 pi. This whole thing. Sin x is less than half. So correspondingly, this corresponds to this, and this corresponds to this. Okay. So hope that gives you a little bit better idea about how this is working out. Okay.
So then how will we combine it? For
Now
final
next thing we have to combine. So see, from this now we are getting this number line. That is how this 2 sin x minus 1 is behaving between 0 to 2 pi. And above we have how cos x is behaving between 0 to 2 pi. So now we'll have to compare these two to understand how the product, like a wavy curve method. Got it now? Like these are two factors of your wavy curve method, but only they are trigonometric factors instead of being just linear factors. Isn't it?
Yes. So now you will compare the factors, right?
Yes. Now I will have to actually put this number line and this number line together and make it a wavy curve to understand where the product is negative, where the product is positive. So cos x also you can just understand how this came. It came directly from the graph of cos x. We draw the graph of cos x that looks like this from 0 to 2 pi. So this was fairly easy. Cos x is positive from 0 to pi by 2 and again from 3 pi by 2 to 2 pi. Whereas in between pi by 2 to 3 pi by 2, the values of cos x are negative. Remember, this one here is the graph of sin x. It's not the graph of 2 sin x minus 1. So now actually we have to put together this real number line and this real number line and understand what their product is doing in terms of algebraic sign. Okay, so up to this step, if there's any doubt, please let me know. Okay, just go through the steps very carefully. This is reasonably complicated stuff. Okay.
So we can just do it quadrant wise. It's a bit lengthy, but it makes sure you get it right. So,
But
X,
even the quadrant beta has to be subdivided, na? Because see in the first quadrant, something else is happening between 0 and 30 degrees and something else is happening between 30 and 90.
so just an example I was giving. So this method is obviously better.
Yeah, we will have to subdivide the interval. So for example, obviously your quadrants are there 0 to 90, but 90 to 180 like that. But within the quadrant also, na, you have to check where each of them are positive and each of them are negative. Like cos x is very simple. It's either positive or negative in an entire quadrant. But this term of 2 sin x minus 1, it has to be subdivided within the quadrant also. Na?
Yes, sir.
Okay. So hope now from this number line or this value, this one is clear. Okay. So now let's see the product. So we are at this step now that f prime x we have written as cos x into this factor 2 sin x minus 1. Now we can make a common number line and understand how each of these factors is changing. So if this is our number line, which as you suggested, let's keep it divided between quadrants first, so that things are a little bit easier. Okay. Now let's first take cos x. So cos x के लिए which were the critical points? Okay, pi by 2, 3 pi by 2. Okay, we saw that for cos x, the graph is positive in the first quadrant, negative in second and third quadrant, and again positive in fourth quadrant. That is as far as cos x is concerned. Now the more critical one, minus 1. Now this had that critical nature that it was positive in a sub-interval of the first quadrant from pi by 6 to pi by 2, and then again from pi by 2 to 5 pi by 6. So this was negative before this, positive in this part, and then again negative in this part. Okay. So now when we look at the product of these two, which is our f prime x, so we can see that in this interval, cos x is positive, that is up to 30 degrees, cos x is positive, but 2 sin x minus 1 is negative. So their product is negative. Now when we go beyond 30 degrees, up to 90 degrees, cos is also positive, 2 sin x minus 1 is also positive. So their product is positive. Now the moment we go beyond 90 degrees, now cos is becoming negative, whereas up to 5 pi by 6, or what we can also write as 150 degrees. Maybe it's still easier for us to understand in degrees before we get used to the radius. Okay. And now you see, when we cross 5 pi by 6, 3 pi by 2, both are negative. So the product is positive. And again, in the fourth quadrant, what is happening? 2 sin x minus 1 is negative, because sin is a negative quantity in the fourth quadrant, whereas cos x is a positive quantity. So the product is again negative. So we have this very interesting kind of set of intervals. So we can see that this function fx will be decreasing, then again increasing here, then again decreasing here, then again increasing here, then again decreasing here. It has that very interesting kind of nature, and they are not symmetric intervals. See, it's 0 to 30, then 30 to 90, then 90 to 150, then all the way from 150 to 270, and then from 270 to 360, one full quadrant. So it has a very asymmetrical kind of pattern. So now from this we can say that the function fx, which was sine square x minus sine x, okay, this function increases from 0 to pi by 6, okay, union with, oh sorry, decreases in this union with pi by 2 to 5 pi by 6, okay, union with this last one, 3 pi by 2 to 2 pi, whereas the function increases in these intervals in between for x belonging to pi by 6 to pi by 2, union with this one now, which is not pi 2, because this interval is actually starting here, so it includes this part. So union with 5 pi by 6 all the way to 3 pi by 2. That's so actually your 0 to 360 is getting broken down into 5 intervals: 0 to 30, then 30 to 90, then 90 to 150, then 150 to 270, and finally 270 to 360. And out of these 5 sub intervals, in 3 of them the function is decreasing, and 2 of them the function is increasing. Okay, so it's a fairly more complicated function, but we are getting this useful information about the function. And later, when we combine this information with the concept of maxima minima, which we are going to learn next, you will see that we'll be in a position to plot the graph of this function also from this information.
So even if we learn that concept, we will have to use this same method only, right, to find the intervals.
If we learn maxima minima,
so if we learn maxima minima, then also we have to use this same number line method to
Not necessarily. No, once we have an idea about maxima minima, we can do a little bit of guesswork about where the function is increasing and where it's decreasing. So we don't always have to make this number line, wavy curve and all this. So in that sense, maxima minima does help a little bit in reducing the analysis we have to do. You know?
Okay.
But I will show you some exceptions later, for which it is very important for you to understand this thing also. That not only how to find the maxima minima, but also to find the intervals where the function is increasing or decreasing. So I'll just minimize this a little bit and take you through the steps above also once more. So from the function, we got the derivative, and we saw that derivative is the product of two trigonometric terms, cos x and 2 sin x minus 1. So by cos x's graph, we directly know. But by analyzing the graph of sin x and this term 2 sin x minus 1, we came to know this second number line, that where this second term 2 sin x minus 1 is negative and where it is positive. And in the final step, we have to now combine these two number lines to understand where the derivative of the function, that is this f prime x, which is product of cos x into 2 sin x minus 1, where that is becoming negative and where that is becoming positive. So when you break it down to the individual steps, you can see each step is pretty straightforward. It is just that you have to combine all of them together, so it becomes a bit lengthy.
Sir, could you please scroll up a bit because
Yeah. Yeah, this part.
yes, sir.
Okay, so done now.
Yes.
Yes, sir.
Okay, so are the final intervals clear to everyone?
Yes. Yes.
Okay, you cross check now. What I've written is correct, no mistake.
Yes.
Okay, so in a few minutes now, we will come back to these two functions also in terms of maxima and minima, and we will justify the intervals we've got also after analyzing their proper graphs with the maxima minima. But before that, let's move on to another interesting concept, which is second derivative of a function. And from that, we'll move on to maxima minima. Okay. So in general, there's also something called nth derivative, but here we'll first start with second derivative. Of a function. So literally what second derivative means, मतलब definition wise क्या होता है second derivative for a given function? It is rate of change of rate of change. The meaning of second derivative is it is the instantaneous rate of change of the rate of change of a function. Okay. So before we jump into the maths, let's think practically in physics what this means. So for example, we know that velocity is the rate of change of displacement. Okay. Don't worry about vectors and scalars just now. Let's just think about it like a straight line motion. So velocity and speed are straight line motion in one direction. And we know that acceleration is the rate of change of velocity. So if we put this in maths language, this is this and this is this. So now if we try to connect this variable with this variable s, what is the relationship we'll get? So acceleration is the second derivative, or we can say acceleration is the rate of change of velocity. So that is what? Rate of change of displacement. So that is the meaning of. So further, if we connect these two now, we will say that A is rate of change of V, which is rate of change. So this operation is only called second derivative. Okay. Now second derivative is given a special symbol. Okay. So we read it as d2y by dx square. Colloquially, that's what we call it, d2y by dx square. But what this symbol stands for is second derivative of y with respect to x. And what this means by definition is that it is rate of change of rate of change. Okay. So in other words, if y is equal to fx, then differentiation of y, in short form, we write the first derivative as f prime x. Okay. So second derivative now becomes rate of change of the first derivative. Which is differentiation of f prime x. So like we write f prime as the shorthand for derivative, like that we use the symbol f double prime for second derivative. So this is the shorthand for second derivative. So through the physical example, I've also told you where it might be useful for us in physics, that one quantity is changing with respect to time, and that quantity itself has a rate of change. Okay. So then there is a meaning of rate of change or second derivative.
So we can directly say it is rate of change of slope, right?
We can say directly that is rate of change of
Slope.
yes, very good. That's correct. Okay. So in terms of graph, we'll see if the original function is having its slope changing in a certain way, then the rate of change of that slope is nothing but the second derivative. Yes, Janvi?
Sir, why have we written shorthand?
Oh, that's a shorthand symbol, na? F double prime, na? That's a shorthand notation for this whole thing.
Okay,
It's
sir.
a short form, na? Like the prime notation, it's a short form. So f prime is the short form for d by dx of fx. So like that, f double prime is the short form of differentiation of f prime x.
Okay, sir.
Shorthand or
Like-
short form notation.
So we can write third order derivative, fourth order derivative also, right?
Yes,
D3
exactly.
by-
So like we have second order or second derivative, like that we can go on differentiating up to what is called the nth derivative. Okay, but we'll keep that for a little bit later, that discussion of nth derivative. First, let's understand second derivative, what it means in terms of the graph of a function also. Okay, so to understand significance of second derivative, let's look at an interesting example. Let's look at the function y is equal to x square. Okay. And from this, we want to find the slope of tangent at x equal to 0, x equal to 1. And x equal to 2. Then also find the second derivative of y equal to x square. Okay. And similarly, we look at the function y is equal to square root of x and do the same thing. Find the derivative and from that the slope of tangent at the same 3 points. And we'll also analyze the second derivative. And we'll see something interesting and contrasting about the two functions. Okay. So just out numerically first, then we'll discuss further. I'm putting up the answers in just a moment. Try it out yourself. Yes, correct, Nisha. Okay, very good. So let me just put up the answers first. So you can see that for this function, okay, the derivative is 2x, and therefore the second derivative, in fact, happens to be a constant, but more importantly, it's a positive constant. Okay. So slope of tangent at x equal to 0, you can see is 2 into 0. Slope of tangent at x equal to 1, you will see will become plus 2. Okay. And slope of tangent at x equal to 2 will become plus 4. Okay. So second derivative is just plus 2. Okay. So this is as far as what I've asked. Yes, Janvi, you have some question, better?
Sir, is there any way to denote the rate of change of tangents on the same graph on which we show the function?
Yeah, I'm coming to that bit. Okay. So rate of change of tangent only is second derivative, but we cannot actually show it in the graph. We have to separately plot the derivative as another function. You understanding? Huh?
Yes, sir.
If my original function is x square, then the derivative is what? 2x. So अभी मैंने derivative को अगर separately plot किया ना graph में, I have the function y equal to 2x. So उसका slope क्या होगा? Second derivative होगा, that is 2. So if you want to understand it in terms of graph, na, we'll have to make two separate graphs. First,
No,
the
sir, I
graph
got
of
it.
y is equal to fx. Na? So uska tangent kya hoga? It will be first derivative. But derivative itself is another function. In this case, it happens to be linear function, but need not always be the case. Na? So like that.
Yes, sir, I got it.
Good. Okay. Now let's analyze this one. So here, my first derivative is 1 by 2 root x, correct? And my second derivative is interestingly going to be what kind of quantity? It's going to be negative kind of quantity. Okay, it is half into derivative of x to the power minus half. So that will become half into minus half. So minus 1 by 4 x to the power 3 by 2. Is this correct?
Yes.
Yes, sir.
Yes.
Second derivative, we should be getting this, correct? But very interestingly, you'll see that the second derivative is therefore a negative quantity. So what that tells me that the derivative itself is decreasing. And that trend you will see over here. What is the slope at x equal to 0? The slope is actually tending, is undefined.
Not defined. Yeah.
But if I take, slightly greater than 0 also, the slope is tending to infinity. Okay. If I take at x equal to 1, now I'm getting plus half or 0.5. If I take at x equal to 2, I'm getting it as what? 1 by 2 root 2, which I can write approximately as what? Root 2 by 4. So 1.41 by 4. So approximately.
The slope of tangent at x equal to 0 is infinity, right?
Now देखो यहाँ पे ना थोड़ा सा प्रॉब्लम है. मेरा डेरिवेटिव क्या है? मेरा डेरिवेटिव है 1/2 root x. So here if I substitute x equal to 0, what I'm trying to calculate is 1 by 2 root 0, which is as good as 1 by 0. Now 1 by 0 is not infinity. 1 by 0 is undefined because it is an illegitimate operation in maths. Okay, but if I say f prime at x tending to 0, so then it's like I'm trying to calculate f prime at x equal to, let's say, 10 raised to minus 30. So that is 1/2 to the power square root of 10 raised to minus 30. So that is 1/2 into 10 to the power minus 15. So that's 10 raised to minus 15 by, sorry, plus 15 by 2. So that is nothing but 5 into 10 raised to 14. Now that's a huge number. So this we can say tends to infinity. What the difference between the two things, no, beta?
Yes.
So remember last time we were discussing about the graph of 1 by x, na, rectangular hyperbola, and how that shows that why the operation of division by 0 is illegal. Apart from this question, there's something else I'm doing now. Okay, so if I draw the graph of y is equal to 1 by x, it's like this. So this graph actually shows you why I cannot define the value of y at x equal to 0. Because if I take the value of x like something like minus of 10 raised to minus 30, the value of y is becoming minus of 10 raised to 30. Okay. But if I take as positive of 10 raised to 30, the value of, sorry, minus 30, then the value of y is jumping to a very huge positive number, positive of 10 raised to 30. But what's happening in the small interval between this point and this point? It's kind of jumping from minus to plus infinity. Na? So that's why we cannot define only what its value is at 0. So that is why division by 0 is an illegal operation in maths. Or we say it is undefined operation. So the derivative at 0 for this particular function is undefined. We won't say it's infinity. But if I take a point tending to 0, we'll say it is tending to infinity. But then again, it becomes a little questionable. Like if it's tending to 0 from the negative side, then again f prime is not defined because square root of a negative number is not defined. But if it's tending to 0 from the positive side, like this one, 10 raised to minus 30, or in this, in this case, I've taken, for whatever reason, I'm taking 10 raised to minus 30 as my favorite number today. But it doesn't matter. We could have taken minus 40, minus 50, minus 100. It doesn't matter. It's tending to 0 on the positive side. So you can see that this tends to infinity. It's very large numbers tending to infinity. Okay. Okay, now coming back to these values, you can see that the slope is decreasing. Forget about the undefined thing, but if it's tending to 0, it's infinite. Okay. So m for x tending to 0 is tending to infinity. So it's decreasing from infinity to 0.5 to 0.35, like that if you go on analyzing. Okay. And what is the other thing that we got? That the second derivative is negative. So if we correlate this with the graph, we'll get a very important result here. That for the function y equal to x square, the shape of the curve was like this. You can see it's curving in such a way that the tangent slope is increasing as we go on. So in general, at any general point x, the slope of the tangent is 2x. So the slope is increasing. So accordingly, now if I draw the graph for the function f prime x versus x, this was y equal to fx, where fx was this. So what is this derivative? It is this straight line. So the derivative is increasing. So what about the derivative slope? So this has a slope of +2. So what that is telling me, that derivative of f prime x or second derivative is +2. And more importantly, the second derivative is positive. That means the derivative is increasing. Okay. Instead of this, if I have, for example, y is equal to x cube. So if I analyze this function y equal to x cube in my graph, that's increasing at an even more rapid rate like this. So I can see that the slope is increasing even more rapidly compared to x square. So here dy by dx or derivative is 3x square. So now if I draw a graph of the derivative, with respect to x, that will be a function like this. So now this one's slope that will be what, 6x. So you can see that's also positive. Whereas if I contrastingly analyze the function y is equal to square root x, the one we were analyzing a moment ago. Now we've seen the graph of y equal to square root x earlier. That's also a parabola, but it's a inverted kind of shape. No? It's like this. It's like this kind of shape. So as your x is increasing from 1 to 2, let's say by the time it becomes 4 over here, you can see that if your function is square root x, okay, then what about the derivative of the function? It was 1 by 2 root x. So the slope of the graph is continuously decreasing. You can see here the slope was 0.5. Here the slope was almost 0.35. By the time you come to 4, the slope will become 0.25. So it has a decreasing slope. So if it has a decreasing slope, what about the second derivative? It will have a negative value. Yes, Nishchay.
Sir, if we take x is equal to infinity, then y will be equal to under root infinity, which will be the
Tending to
same as
0.
how?
Acha, y, it will be correct. For the function root x, y will be tending to infinity. For this function, yes. But I'm saying for the derivative will tend to 0. So that means this curve will continue going to infinity, but as it goes to infinity, it becomes almost flat. You understand me? Because the derivative tends to 0.
Yes.
Okay. So you can see that x tending to infinity, y tends to infinity. But what about the slope? The slope, however, tends to 0. So it curves in such a way that it flattens more and more and more. So by the time you're reaching infinity, it's almost flattened to a straight line. That is the information that the slope is giving you. Now from the slope, what is the information of the second derivative? F double prime x, or derivative of f prime x, or second derivative. That was minus 1 by 4 x to the power 3 by 2. So you can see that this has a negative value. This is negative. Why? Because this thing is decreasing. Slope is decreasing. So for the function, if the slope is decreasing, that is f prime x is decreasing, that means the second derivative is what type? It is negative. F double prime x is less than 0. Yes, Nishchay.
Sir, how can we visualize this? I mean, the rate of change is.
So see, one way of one is directly in front of you. Okay, you can see the difference between the trend of the graph y is equal to x square and the trend of the graph y is equal to root x. X square में उसका curve देखो कैसा है? It's of increasing slope.
Yes.
You can see now. So this will have second derivative positive because the slope is increasing. Whereas this sort of a graph, you can see the slope is decreasing. So what can we say about second derivative? It must be negative. Understood now how we can be?
Y is increasing at a slower rate as compared to x, right?
More importantly, we'll say that the rate of change of y is increasing. You understanding that the tangent slope is increasing. That happens for which type of shape? This kind of shape. So the rate of change of y with respect to x is increasing. Whereas
But
if I have this kind
y
of shape,
equal to root x.
this kind of shape, okay, opposite is happening. You understanding me?
So here in the second case, y is increasing at a slower rate as compared to x, right?
No, y is increasing at a rate which is slower or faster. That how you can check for 2 points? Only by checking the derivative. If dy by dx at one point is greater than dy by dx at another point, that means the rate of change is greater. But now we are talking about how the slope is changing. That is how dy by dx itself is changing with respect to time, with respect to x. Now, not how y is changing with respect to x. Understood the difference between the two now?
So y is means dy by dx may be positive, but the rate of change of that slope is negative, right?
Yes, exactly. That's what's happening in this second graph. You can see the slope is positive at all these points, but the slope itself is decreasing in value now. So that means what is the second derivative? It's negative.
Okay.
So we
No,
can
both
also
in
say
the.
right that.
Sorry, beta,
Sorry,
come again.
no, sir, I interrupted you. Sorry. So please go on.
So in both the graphs, now y is equal to x square as well as y is equal to root x, the derivative is positive. So you can see y is increasing with x. But in one of them, the slope is increasing. In the other one, the slope is decreasing. So that is why in the one where the slope is increasing, the second derivative is positive. In the one where the slope is decreasing, the second derivative is negative. Okay, are we clear about the difference of the two?
Yes.
Yes.
Okay. Now, of course,
So
we could have
also,
yeah.
So we
Also,
can also say that when the curve, it's facing upwards, at that time the second derivative is positive.
correct. In fact, in mathematics, this is given a special name. This type of curve is called concave upwards, and this is called convex upwards, because when you see it from upwards, you see a cave, you see a concave shape. Whereas when you see this from above, you see a convex shape. Okay. So that's the difference between this shape here. It is concave upwards, and this shape is convex upwards. Okay. Is this clear now?
Yes, sir.
Okay. Now, next example, let us look at this function y equal to 2x minus x square. Okay, so let us look at dy by dx and second derivative also. Okay, and then let's analyze slope of tangent at x equal to 0, x equal to 0.5, x equal to 1, x equal to 1.5, x equal to 2. Okay, let's analyze all these things. Okay. So let's start with dy by dx. So y is equal to 2x minus x square. So the derivative of the function is 2 minus 2x. That's correct. So from this we can see that the slope at x equal to 0 is going to be how much? Plus 2. Just substitute x equal to 0 in this. You can see the slope of the tangent at x equal to 0.5 will be 1 minus 0.5. That's 0.5 into 2, so plus 1. The slope of the tangent at x equal to 1, you can see is becoming 0. See, the slope of the tangent at x equal to 1.5 is minus 0.5 into 2, so that's minus 1. And like that, the slope of the tangent at x equal to 2 is becoming how much? 1 minus 2, so that's minus 1 into 2. Okay.
Sir,
Yes, are these values correct?
so slope of tangent should be the second derivative, right?
नहीं, slope of tangent बेटा, slope of tangent तो first derivative का value होता है ना?
The rate of
Why
change
are
of
you getting
second
confused,
derivative.
Ibrahim? For any function y equal to fx, okay, the slope of tangent is basically what? At any point you draw the tangent line and you find its tan theta, no? So what is that? That's the value of dy by dx at the point.
No, sir, I thought slope of tangent should be rate of change of tangent. So, yeah.
Hey, don't confuse the two, na? It is slope of the tangent is just the rate of change of the function, na? So for a
Okay, sir.
function y equal to fx, na, what is the slope of the tangent? It is the value of dy by dx at that particular point. Okay, so it is f prime of that particular point. Got it now?
Yes, sir.
Okay. Achha, now let's come to this. What? So these values are correct, the ones I've written here. Yes.
Yes.
Okay.
Yes, sir.
Okay, this graph is not related to this question. This is separate. Okay. Now let's come to second derivative from this. So what is d2y by dx square? It is derivative of the first derivative. Okay. So this only was my f prime x. So I need to differentiate this now. So it is 2x minus x square ka derivative. Okay. Oh, sorry. My mistake. The derivative is this one. Okay. So I need to differentiate this function now. Need to differentiate this function 2 minus 2x. So that is what it is negative. Okay. Now remember what was the information that second derivative used to give us? It used to give us information about the slope of the tangent. So what we are analyzing here, that this function it has second derivative equal to minus 2. So what that tells me, that means the slope of tangent, okay, is always decreasing. As x increases, because it has a uniform value for all points. It is a uniform negative value for all points. So what that means, that it is always decreasing for all values of x. So at least in this set that I've between 0 and 2, you can see that m is all the time decreasing. As you're going from 0 by increments of 0.5, you can see m is decreasing from 2 to 1 to 0 to -1 to -2. So the second derivative should be negative now, because the slope itself is decreasing. Okay, so now let's put together this information in graph. Okay, so let's start with a graph of y is equal to fx, which was my original function. It was 2x minus x squared. So this was my original function. So I can factorize this and write it as x into 2 minus x. So again, through your wavy curve method or whatever, you can understand that 2 is a critical point for this. And the value of the function is positive in between 0 and 2, and negative before 0 or negative after 0, after 2. So the graph of this function is something like this. It's a parabola. Okay. Now in this graph, let's put the information about the slope. So what was the derivative of the function? It was 2 minus 2x. So what we'd seen, that the slope at x equal to 0 was plus 2. The slope at x equal to 1 was 0. The slope at x equal to 2 was minus 2. In between also we had seen the slope at x equal to 0.5 was plus 1. The slope at x equal to 1.5 was minus 1. So see that information in this graph over here. It means that if I draw the tangent here, the slope is how much? It is plus 2. But by the time I come to this point, which is x equal to 1, the slope of the tangent is becoming how much? It's becoming 0. And likewise, by the time I come to x equal to 2, the slope of the tangent has further decreased to minus 2. At this point, 0.5, the slope of the tangent is plus 1. At this point, 1.5, you can see the slope of the tangent is how much? Minus 1. So see how the tangent is changing its slope. It's changing its slope from 2 to 1 to 0, minus 1 to 2. So what we know about the second derivative, therefore, the second derivative has to be a negative value, because all the time the slope is decreasing. Even if you compare from here, the slope is decreasing. And if you continue after this also, it's becoming a larger and larger negative number. So the slope is decreasing. So see the shape of the graph, it is convex when you look from upwards, because the second derivative is negative. When you see from above, it's a convex graph. The shape is such that the slope is continuously decreasing.
Excuse me, sir.
Yes, tell me, beta.
Sir, can you scroll up for just a second?
Yeah.
Yeah, done, sir.
Okay. So the correlation of the information that we have got now for the slopes at the various values above and the second derivative, that it was in fact equal to -2, but more importantly it's a negative value throughout. That is clear now in how it's showing up in the graph. You can see that if I compare any 2 points on the graph, if I go further down the x-axis, the slope of the tangent should decrease. It's decreasing from -1 to -2 to -3 to like that, and on this part it's decreasing from 3 to 2 to 1 till it comes to 0, and then it becomes negative. So continuously going down the x-axis in the positive direction, the slope of the tangent is decreasing. Why? Because the second derivative is uniformly negative. So hope this point is clear to all of you.
Yes.
Okay, now just think what would happen if I instead had this function. Instead of 2x minus x square, I had x square minus 2x. What would happen to this one? Here the derivative would be 2x minus 2. Okay, and the second derivative would become plus 2. Now, okay, now if you think about the graph of this function, it's just the opposite of that one, because you just multiplied it with minus sign. Earlier we've taken 2x minus x square, now we've taken x square minus 2. So I've just multiplied that graph with a minus sign, or that function with a minus sign. So it should have the reverse kind of behavior now. It should have this kind of behavior. So this point is 2. So now if you analyze here, you will see that the slope of this graph, this time at 0, you will see that the slope is -2. At 1, you will see the slope is -1. At 0.5. At 1, it will become 0. At 1.5, it will become +1. At 2, it will again become +2. So here you can see that happening. Here the slope is negative, but here it is slightly more gentle. Still negative, but slightly more gentle. By the time you're coming here, the slope is becoming 0. So here the slope is increasing. So what we can say about second derivative? Second derivative is positive. So when you see the graph from above, you are seeing what kind of shape? It's concave shape.
Okay.
So see the contrast of this one with that one. Both are quadratic functions. In fact, they're both very closely related. I've just multiplied this with a negative sign, so it's got inverted. But immediately see the difference in how the slope is behaving. Here the slope as you go down the x-axis is continuously decreasing. So the second derivative was negative. Whereas when we come to this example below, because I've just inverted it, you can see the slope is continuously now increasing. It's going from -3 to -2 to -1 to 0 to +1. Okay. So here the slope is continuously increasing. So accordingly, second derivative is positive. Okay, so this graph is also clear to know all of you now. All right. Now recall that earlier example I had taken. Y is equal to x cube minus 3x plus 2. We had drawn a sort of rough graph of this. And from that, we had seen that the shape of the graph was something like this. Shape of the graph was something like this we had seen. Okay. Because here, if the function was x cube minus 3x plus 2, the derivative of the function was 3x square minus 3. Okay. And the second derivative of the function became 6x. Okay. Now you can see something interesting here. What is happening in this part? The slope is going from some large negative value to a smaller negative value to 0. Oh, sorry, large positive value to a smaller positive value to 0. So in this part, what we can see, the slope is decreasing, isn't it? So you can see what is happening to second derivative. Second derivative is negative for x less than 0. 6x is a negative number for x less than 0. So that means for x less than 0, the slope of the function, that is dy by dx, is decreasing. You see that happening in the graph. Okay. Whereas if you analyze this part of the function, here you can see the slope is 0. Then here the slope is becoming larger and larger positive value. Here it's becoming a smaller negative value. So in this part of the graph, you can see the slope is now increasing. And again, you can see this, that the second derivative, f double prime x, is positive for x greater than 0. So what that means, that the slope increases for x greater than 0. So this part of the graph, when you look at it, it looks like a concave shape from above. This part of the graph, when you look at it, it looks like a convex shape. So this function has both the features. Part of the graph is concave, part of the graph is concave. In part of the graph, the slope is decreasing. In part of the graph, the slope is increasing. Okay. Now this sort of a point where the slope has become 0, this point here, you'll remember, was -1, and this point here was 1. Okay. So you can see for this particular function, at x equal to -1, in this case, what is happening? The derivative of the function is 0. But what about the second derivative of the function? It is what type? It is negative.
So just before that instant only it will be negative, right?
नहीं, second derivative कह रहा हूँ बेटा. Second derivative देखो कितना है, 6x है ना. So at -1, what is the value of the second derivative?
Acha.
Negative.
You can see now it is -6. So what is the nature of the slope now? See, just before this, the slope would have been like, let's say, -0.2. Then it's becoming 0. Then it's becoming +2, +0.2. So what is happening to the slope? The slope is, sorry, it is +0.2 and it's like this. So what's happening to the slope? The slope is decreasing. So the second derivative is negative. Just because the slope is 0 doesn't mean that it is remaining flat. No, it's flat only at that instant, but the slope is actually from a positive value to 0 to a negative value. So what about the rate of change of slope? That should be negative now, and that is the information that we are getting. It's clear now?
Yes.
Okay. Whereas see what is happening at the point +1. At the point +1, the slope is 0, because again 3x square minus 3 is 0. But what about the second derivative? It's positive. Okay. At x equal to +1, the derivative of the function is 0. But the second derivative of the function is positive. It's equal to +6. Okay. Now in the graph, what is the difference between the 2 points, -1 and +1? -1 is a point where the graph has reached a peak, whereas +1 is a point where the graph has reached a dip. Okay. So whether a graph reaches a peak at a point or it reaches a dip at a point, the slope is 0 at both these points. Okay. But the difference is the slope is changing from positive to negative here. So the second derivative is negative over here. The first derivative is 0. Whereas here what is happening, the slope is changing from negative to 0 to positive. So second derivative is what type of quantity? It is positive, whereas first derivative is 0. Understood the difference between any peak point and any dip point? You think of any graph which has this behavior, like you think of the graph of cos x, for example. Cos x varies with x like this. So what is happening at this point for cos x? At 0, the slope is 0. Okay, but the slope is changing from negative to 0 to positive. What is happening at this point? The slope is 0. The slope is changing from negative to 0 to positive. So at this point, the second derivative is what type? It is positive. At this point, the second derivative is what type? It is negative, because the slope is changing from negative to 0 to positive. So f prime is 0, but f double prime is negative here. F prime is 0 again here at pi by 2. Sorry, at pi. Okay. But what is happening? The second derivative is positive. So like this, whether it's an algebraic function or a trigonometric function or a combination function, any point where the function reaches a peak, this is what happens. The slope is 0, but the second derivative is negative. And any point where it reaches a dip, this is what happens. The immediate tangent has a 0 slope, but the trend of the tangent is that its slope is increasing. So the second derivative would be positive. Have you understood this, people? Any doubt?
Yes, sir, understood.
Okay, so you'll see that this sort of point is called a local maxima. And this sort of point is called a local minima. So this becomes our definition of local maxima and local minima. Okay, so for any function, yes, Nishchar, you have a doubt?
So means it's just like a wave, right? Crest,
Any
center of-
function's curve in general, it can be a wave. Okay, so if it is a wave, there should be some point where it reaches a peak. So at such a point, we say the function reaches a local maxima.
Yes.
So could you say that again?
Yeah, just a minute. Just give me a moment, guys. Are you getting the shared screen, or is it gone from the?
No, sir, it is.
Is there? The screen is there?
Yes.
Yes, visible for me.
Okay. Now it's gone?
Yes, sir.
Yes, sir.
Just a minute. Yeah. So coming back to this, you can see that whenever a function's graph, it reaches a sort of a peak point like this one over here. We call it a local maxima. And what happens at the peak point? At that particular point, if we draw a tangent, its slope is 0. But what is the behavior of the f prime x? It is changing from from positive to 0 to negative. So second derivative is what kind of quantity? It is negative. Is this clear now?
Yes.
Yes. Whereas the second type of point like this over here, it is called a local minima because it is reaching a dip. Now what happens at the local minima? Again, at that particular point, the slope is 0. But what is the behavior of the slope? It is going from a point before it where it was negative to a point after it where it is positive. So that means the slope is increasing. So increasing slope means what? Sex positive. Okay. So this is a point where slope equals to 0 and slope increases. So that means second derivative is positive. Whereas this is a point where slope is 0, but slope is decreasing. So that's why my second derivative is negative. So hope this is clear now, this definition, right?
Yes.
Okay. So from this we can generalize and say that if I have any function given to me, so for any function y equal to fx, okay, if dy by dx is equal to 0 and second derivative d2y by dx square is equal to negative at some point, let's say x equal to a, then it means that the function fx has a local maxima at x equal to a. Because what is happening at x equal to a, the slope has value equal to 0. Okay, and the slope in general is decreasing. So that means the shape of the graph is looking like this. This is how fx is looking like. And this is the point A. The slope is 0 at that point, but it has a value which is changing from positive to 0 to negative. So its value is decreasing. The second derivative is negative. Understood this point now?
Yes, sir.
Yes.
And in contrast to this, if we have this sort of a point now, so what is happening over here? At this particular point, the slope is 0. Okay. dy by dx is 0. But it is changing from negative to 0 to positive. So second derivative is what kind of quantity? Positive. So this becomes a local minima point. If dy by dx is equal to 0 and second derivative is positive at a point x equal to b, then it implies that the function fx has a local minima, this sort of point at x equal to b. So on my x-axis, this point would have been b, whereas here on my x-axis, this point would have been a. Okay, and this is the function fx. So you can see the above example that we had taken, the cubic function, it had both a local maxima and a local minima. The local maxima was occurring, local maxima was occurring at the point -1. The local minima was occurring at the point 1, because at this point you had that feature that the slope is 0, but the second derivative is negative. Whereas at this point, what was happening? Okay, at x equal to +1, the slope is 0, but the second derivative is positive. So this becomes the property of a local minima. Okay, and this becomes the property of a local maxima. Point. Yes, Janvi, you had some question, beta?
Yes, sir. Sir, if
Yeah.
we want to find the number of maxima and minima in a function, we can actually just differentiate it and then we can factorize it. So all the roots of the
Yes. The roots of the derivative are collectively the points where you have either local maxima or local minima.
minimum.
Okay, so we will see that collectively these points are called turning points because the behavior of the function is turning. It is going from increasing to decreasing or decreasing to increasing. So
And sir,
turning point.
So they occur in pairs.
Not necessarily, they can occur. So for example, if you have a power 4 or degree 4 polynomial, then the number of turning points will become 3. So then either 2 of them are maximas and 1 is minima, or 2 of them is minima and 1 is, got it now?
Yes, sir.
So for polynomial functions, if you have a polynomial of degree n, then its derivative is of degree n-1. So potentially how many turning points we have? Up to n-1 turning points. So we have a polynomial of, let's say, degree 100, then there are up to 99 turning points. And any sort of combination is possible, that so many out of 99 are maximas and so many out of 99 are minimas. Like that's a very extreme case. But at a simple level, for example, quadratic function has degree 2. So that means its derivative has degree 1. That means it has only one turning point. So that's why you see a parabola has only one vertex. It doesn't have a peak and a dip. Either it'll have only a peak or it'll have only a dip. But a cubic function in general can have both a peak and a dip. Right, but I hope you're following.
Yes, sir, I got it.
Yeah, so if you go through the examples we've done today, like that quadratic function x square minus 2x, then again 2x minus x square, then the cubic function that we took, then the more complex sine square function that we took, sine square minus sine x. We'll analyze it again next time. You will see that all these things will become clearer as you start applying them to the particular examples. Okay, so we'll take this slowly and easily. Don't worry, we'll do a lot of examples next time also. But hope up to the definition is clear to all of you, that what is a point of local maxima? It is a point where these two conditions must be satisfied. It's not an or condition. Derivative 0 hona chahiye, and along with that, necessary and sufficient condition is that derivative is 0 as well as second derivative should be negative. Whereas if second derivative is positive, where the derivative is 0, then that point becomes a local minima. Okay. So this is the definition of a point of local maxima and the definition of a point of local minima. Yes, Nishya?
Sir, in a graph, we can have many maximas and minimas, right?
Exactly.
At the same time.
Correct. Can happen. Like for example, if you take the sin x graph only, for x going from minus to plus infinity, it has infinite number of local maximas, infinite number of local minimas.
Yes.
Or if you take a polynomial with very large degree, like a polynomial with degree equal to 50, it'll have up to 49 turning points.
49. Okay, sir.
Okay, people. So that's it for today's session. Okay.
So what if the maxima and minimas are if you are talking about a power of 49, then what if they are repeated numbers for which dy by dx is equal to 0?
Yeah, they can be repeated numbers also.
So we will not have 49, right? We will have.
That's why I said up to 49.
Okay,
like for example, you have a cubic function, and when you differentiate it, you get a quadratic function, right? Now that quadratic function might have repeated root. That quadratic function might be of the type x minus alpha whole square instead of x minus alpha into x minus beta. So in that case, that cubic function has only one turning point.
Yes, got it.
So ऐसा भी हो सकता है ना? So all these possibilities are there. So in general, we say if the degree of the polynomial is n, then you have up to n minus 1 turning points. It can be less than n minus 1 also, but the maximum number of turning points possible is n minus 1.
Means maxima and minimas, right?
Yes, turning points are the collection of points which are like the superset of maxima plus minimas.
Okay, sir. Thank you, sir.
Okay. Okay.
Bye, sir.
Okay, all the best, people. I will be sending you an assignment again this week for basics of maxima minima discussion also, and continue with the assignment in your module also. Yes, after I finish this differential calculus, I will suggest a reference book for you people. Okay, just let me finish maxima minima properly in the next lecture. Then I will suggest the proper reference book for practicing not just calculus but in general for physics.
H.C. Verma.
H.C. Verma is good for certain level of questions, but then there is other types of books also. Like for theory, there is Resnick Halliday. Then for very good level questions at Olympiad level, there is Irodov. Otherwise, there is D.C. Pandey also, or Sengage. Many different types of books are there. So I will spend some time in discussing about what are the reference books you can go through, and in which type of reference book, what type of work you should do, like where you should read your theory from, where you can practice questions from, etc.
Okay, sir. Thank you, sir.
Okay, thank you.
Bye, sir. Thank you.
you.
Okay.
Thanks a lot for By-Shome.
Okay, bye people.